Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is the AAS Journal Author Series. And I am super happy to have Paola Alvarez-Hurtado with us today. Hey, Paola.
Hi, friend. It's great to hear you.
Oh, good to hear you. Well, first of all, thank you very much for agreeing to talk about your super lovely article. That's great. I'm happy you're doing it. And Paola, where are you located at?
I'm in Mexico City. I'm in Astronomy Institute of Universidad Nacional Autónoma de Mexico, also known as UNAM.
Yes.
and this is my office.
I love your blackboard there to the left there. It looks like we have some appropriate astro scribbles on there. So very good. Nice. Let's see, it is June 30th, 2022 as we record this. So summer is probably in full swing in Mexico City. And if I remember right, this is also the rainy season in Mexico City, yeah?
Yep, but also the seasons of bougainvilleas and houses finches.
Very cool. So the same phenomena happens in Phoenix, where I'm at. We get our rains in June, July, August is when that happens. And yes, the bougainvilleas, and I have 3 of them, are doing very well. They're going great. Paola, what's your position there at UNAM?
I'm a PhD student. I'm on 3rd year, so almost in last final year.
Oh, very good. So then very soon we get to call you Dr. Paola. Very awesome. Thanks for doing that. Very good. Awesome. And speaking of all that, Paola, what do you like to do for research?
Well, I'm focused mainly on chemical abundance on nearby star-forming galaxies.
Cool.
So that's my work.
That'll be an awesome thesis. And part of that thesis is probably going to be this very lovely APJ article. It's open access, people. You can grab it for free. Go ahead and get it. Which galaxy property is the best gauge of the oxygen abundance? And Paola, take us away.
Well, this paper is trying to answer the fundamental question: is the stellar mass the main galaxy's parameter that correlates with oxygen abundance? So why do we direct our attention, to this topic? Among the different metals in the universe, oxygen is the most abundant one after helium and nitrogen, and it's a byproduct of the internal reaction in stars, but also it's generated in a supernova explosion phase when it happens. So once a certain amount of oxygen is expelled to the interstellar medium, it enriches the next generation of stars. Therefore, it is an expected relation between the stellar mass and oxygen abundance.
Okay.
However, the relation between these 2 parameters, known as the mass metallicity relation, or MCR, has been explored for almost 40 years. More recently, in 2004, some authors made the first systematic exploration of the relation for more than 53,000 star-forming galaxies, showing that these 2 parameters exhibit a tight relation. But if the oxygen abundance is related to recent star formation event, what about the amount of coal gas or even the number of stars? So in between 2008, 2010, some studies strongly suggest that the star formation rate plays an important role in shaping the mass metallicity relation. Those works show that the mass metallicity scattering decrease when we include a second term related to the star formation rate. Other authors have claimed that the existence of secondary relation with both the gas fraction and atomic or molecular gas mass in context is already possible.
Okay.
And other propose that secondary relation may depend on the calibrator. However, all these studies use single aperture spectroscopy data, which limits the information to an average quantity within a given aperture, since its physical size varies with the distance of each galaxy.
Got it.
On the contrary of some recent studies, claim that the oxygen abundance depend on the star formation rate at fixed stellar mass based on spectroscopic data,
Okay.
arguing that their results are consistent with secondary dependency of star formation rate derived with single fiber spectroscopy. So what's happening? What are there other parameters related to oxygen abundance or not? And secondary relation depends on the calibrator. And well, this is here where our study begins. To address all these questions, we, and aforementioned issues, we use spatially resolved data from the extended Khalifa survey, complemented with cold gas from Apex survey, and H1 observation from half of the galaxies in our sample. And if we scroll to figure 1,
doing those science cubes, and there we go. Figure 1, star formation rate. There we go.
We can see that our data compiles almost 300 galaxies in an active star forming phase. All these galaxies are located in the nearby universe up to redshift 0.008.
Okay.
And well, our sample extending a wide range of stellar masses and star formation rate. So in the right column of this same page, we will find a list of all parameters incorporated in this study. Some of these parameters were calculated using a dust to gas proxy. Others are derived directly from data. In total, we explored 29 physical properties, such as the total gas fraction, molecular gas mass, a new variable that we call cosmological time, in which galaxies reaches some % of its actual stellar masses, denoted with a T in capital letter, and following by a number according to this percentage, 50, 80, 90. And this parameter is important because imply that the stellar mass can be considered as the final product of the star formation history. But also we work with star formation rate, morphological type, ionization parameter, dynamical mass, concentration index, gas mass, cosmological distance, star formation efficiency, among others.
Wow. Okay.
Yeah, this is a total of 29 parameters.
Okay.
So to derive the oxygen abundance, we use 6 different calibrators based on a strong line method to address the possible metallicity calibration discrepancy. And as a first step, we explore whether there is any parameter that could correlate strongly with the oxygen abundance other than the stellar mass. And we use the Spearman correlation coefficient with the 6 different calibrators. And to do this, we summarize our analysis in figure 2.
Ooh, nice. Very nice. Okay.
In this figure, we show the ranking order according to the correlation coefficients. As you see, the x-axis correspond to the Spearman correlation coefficient, and y-axis are listed all parameters that we use. As we can see, there is some degree of fluctuation in the ranking order. Each symbol represents a value according to one calibrator. In particular, we see that this fluctuation is mostly appear for parameters with low values of Spearman coefficient. So we find interesting that without prior judgment on which parameter produces a significant effect on the mass metallicity relation, this exploration confirms that the stellar mass is the one of the best tracer of the oxygen abundance, at least for our sample or data set. Furthermore, we find that the ranking is followed not by parameters not directly related to the stellar mass. In fact, there is a strong correlation with parameters that directly trace the shape of the star formation history, as the T90 or T80 parameters.
Here, yes.
And also with the morphology. And
Okay.
we find that the lack of significant correlation between oxygen abundance and certain parameters that have been frequently claimed to have a significant impact on chemical enrichment in galaxies, such as the star formation rate or the specific star formation rate. And it is worth noting that all these results are broadly independent of the adopted calibrator.
Okay.
So, however, we are aware that some of these parameters that appear in the ranking also present a strong correlation with stellar mass. For example, the total gas fraction or the star formation main sequence that correlates with the star formation rate. And therefore, the real effect on the abundance should be explored after removing the primary,
okay,
I mean, the strongest relation with the stellar mass. For doing so, it is important to determine the relation between the oxygen abundance and the stellar mass. As we mentioned earlier, this relation is known as the mass metallicity relation. In the best possible way, prior to exploring any possible secondary dependency.
Yes, I'm with you.
So in order to remove the primary stellar mass dependency, the next step is to characterize the mass metallicity relation. However, different procedures have been adopted in the literature to parameterize the relation between these two parameters. And thus, we explore different statistical criteria, such as binning scheme, outliers effects, fitting techniques, and explore different functional forms.
Cool.
Considering each of these fitting strategies, we perform a total of 24 fits. And according with our exploration, outliers could affect the binning criteria, inducing on the representation of the number of galaxies for a given stellar mass in less populated regimes. Moreover, we know that depending on the fitting technique, the shape of the mass metallicity relation is significantly different for the same functional form, as we can see in the figure 3.
Figure 3.
Please.
I'm with you. Figure 3, there's some of our coefficients, and figure, ooh, there we go. Okay. Yes.
Well, in this figure, we look the green and the purple fits are different forms, but it's the same functional forms according to linear, exponential, or polynomial function.
Okay.
So what should we highlight from this image? Well, we find that all data statistical treatment could generate different description and consequently imply different chemical behavior. So for all these 24 fits, you may be wondering how we choose the best fit.
Okay.
And that brings us to figure 4.
Very cool. There's our parameterizations. And figure 4, there we go. Contours and the delta MZR. Okay.
Okay, well, to choose the best fit among the 24 combination, we compute residuals of the oxygen abundance as the difference between the observed and fitted data.
Okay.
We denote these residuals with a delta MCR, and these residuals allow us to quantify a fit's reliability, since we must ensure that the metallicity residuals do not depend on the stellar mass. For this part of our work, we apply an agnostic examination of the goodness of the fit. In summary, we find that a polynomial of third order is the functional form that best shapes the mass metallicity relation for our sample of star-forming galaxies, regardless of the calibrator, since present the least dependence on the stellar mass.
Okay. Okay. Got you.
So,
got you. You're trying to do the complete subtraction. I'm with you. Yep.
Okay. So in figure 5, we compare our best fit mass metallicity relation with similar results extracted from literature. And we can observe an agreement between our results, the red line, and those reported in other works. However, in our study, we find variations in the shape of the mass metallicity relation using a Monte Carlo approach, a low mass regime. This variation is represented with the red shaded region at the end of the polynomial.
Okay.
So we cannot rule out either a flattening or decrease of the oxygen abundance along massive galaxies.
Okay.
Even with this variation, the polynomial is still the best characterization of the mass metallicity relation, since we have ensured zero dependence with the residuals on the stellar mass.
Yes.
So now we need to figure it out if the 29 parameters mentioned before are still strongly correlated with the oxygen abundance, or if their correlation is due by the stellar mass. And that takes us to figure 6.
Figure 6, 3.4. And there we go. We got some contours. There we go.
Yeah. Well, this figure summarizes the result of this analysis.
Got it.
This figure shows the distribution of the mass metallicity residuals as a function of the first 12 parameters that present a mild correlation with the residuals of the oxygen abundance.
Okay.
These panels are sorted according to their average correlation ranking.
Okay.
And show us that the residuals of the MCR does not significantly correlate with any other physical parameters. And how do we quantify this? Well, we use different statistical criteria, chi-square analysis, correlation coefficient computations,
Yes.
and even a scatter reduction.
Yes.
In no case do we find a strong correlation nor a scatter reduction. In fact, the largest correlation factor is around 0.3 and is related to a weak or no correlation. So all this result is again independent of the calibrator, as summarized the figure 7. Please.
There we go. Figure 7. Very good. Okay, here's our. Okay.
This figure is very crowded, but in summary, all correlation with the residuals are weak, even for those parameters as the star formation rate or those related with the cold gas component, such as the molecular gas fraction, both inferred directly from edge apex data or derived using extinction-based data.
Okay.
But the figure 8 gives us a clear image of what's happening.
Yay, okay, we took that out. Good, okay.
In this figure, we find that the new ranking of parameters, once again, the main dependency of the oxygen abundance with the stellar mass has been completely removed for each calibrator.
Yes.
And what can we conclude from this figure? When we remove the main dependency on the stellar mass, the correlation coefficient between the residuals and all parameters decreases significantly. However, some parameters may have some secondary impact on shaping the oxygen abundance in star formation galaxies. Apart from the observed gas fraction inferred from edge and apex data, the parameters that domain the first places in the ranking, or in other words, that correlate the most with the residuals, are related to the project distance of the galaxies. This is redshift or cosmological distance, suggesting a possible evolution of the characteristic oxygen abundance in nearby galaxies.
Well, that would be interesting.
So,
very cool. Very cool. Okay.
Yeah. So we also know that parameters related to the galaxy evolution could also play a role in shaping the abundance, as the morphology or parameter related to the star formation history. As we mentioned, the 90 ratio with T50, among others.
Okay.
So in summary, this analysis suggests that correlations derived directly using oxygen abundance and the 29 physical parameters reflect an intrinsic relation between this parameter and the stellar mass, or even themselves, rather than a particular dependency on the oxygen abundance itself.
Yes.
Although we did not find evidence of a strong correlation, we do not rule out the component in the interstellar medium in shaping the oxygen abundance.
Fair enough.
So we suggest that at least in star-forming galaxies, the chemical enrichment on the interstellar medium is tightly connected to the star formation history.
Nice.
And in figure D1, in appendix,
Oh, the appendix, yes. So we go down, we got the shape, what
we
drives.
can see a figure, a very beautiful figure.
There's a very beautiful figure. This one?
No, the other one, D1.
Big one. I missed
Below,
it.
below.
Oh, below. Sorry, my bad. Bad driving. Bad driving. Oh, there we go. Now we got all of them again.
Well, this figure is mixture between the last two figures when we calculate the correlation coefficient between the oxygen abundance and these parameters, and well, using the correlation coefficient, and when we use the residuals, and it's clearly the effect on when we remove the stellar mass, because all the correlation coefficient decrease.
Yes.
So we look an after and before and an after schemes. So that's a big idea of my work is.
Well, that's a pretty awesome big idea. I think that's fantastic. Very good. Okay. Awesome. I got it. Very good. Ooh, so I got a good question for you in a minute. Okay. So that was awesome. And Paola, thank you very much for walking us through your very lovely article.
Thank you again for the opportunity.
Sure. So you kind of hinted at it a little bit there, or at least I had the question as we got to that last one. So where do we go, let's say, over the next 2 to 5 years on this topic? Is there additional data to take from maybe some new telescopes? Is there theoretical work that can be done? Just sort of where do we head? You know, maybe it's the next paper or chapter in your thesis or whatever it may be, but where do we go? Where do we head? Okay,
well, one of the things that could be done in coming years will be to increase nearby galaxy samples based on the integral field spectroscopy technique, including lower stellar and masses galaxies. In addition, increase complementary observation at other wavelengths, whose data can be integrated at the same aperture that the main sample.
Right.
Indeed, a larger sample could even reveal more details about possible secondary relation with the molecular gas mass, but also will reveal whether the polynomial fit of the for the mass metallicity relation describes a second flattening or a decrease for low mass galaxies, or maybe just an artifact. So once we are able to determine the shape of the mass metallicity relation at the very low masses, the next step is to unveil a physical scenario that explains it. And in this regard, it will be helpful if we join ALMA and amusing data, or MANGA with Riemann telescope.
Okay.
With this data, we could obtain more robust results. And so let's see how this topic evolves.
Let's see. I'm excited. Very cool. Paola, thank you so much again for walking us through. And that will do, everyone. And I hope this made your astronomy day just a little bit better. And we will see you on the next one. Bye-bye.